Pleasure to introduce our speaker today, Dr. Rachel Bezanson. She's reminded me she's been a postdoc for about 23 days, so that's one day almost per person in the room, I would imagine. She's been a postdoc. She did her PhD work with Peter Van Dockum at Yale before moving to Stewart Observatory, a famed location for many great astronomers before her. No doubt she will add to that now as a Hubble Fellow at Stewart. She's here today telling us about, actually, I think some new work you're doing involving the mass fundamental plane at Redshift 2. And your title here is pretty provocative, so I'll let you take over.
Yeah, so thanks for having me here. I've never been to Texas before except at the airport, so this is kind of exciting.
So howdy!
But I am from Colorado, so I get the Western.
It ain't the same.
But I know it's not the same. So today I'll talk a little bit about provocative stuff, but I'll start by kind of setting the stage. I'll spend the first half of my talk setting the stage for this, and I'll talk a little bit about new stuff that's nearly published. But I'll start really very much at the beginning. Oh, we're getting cut off at the top too. The top says that this is the deepest look at the universe.
We can actually see it.
You
It's
can?
on the
You can
light
see it.
thing.
Awesome.
Yeah, we just have to put it together.
Okay, so when we look into the sky, pretty much as deep as we look, we see many, many galaxies. And they come in all different flavors and colors and shapes and sizes. And the main question that kind of drives my research is, how do we look at the galaxies that we see and first identify them, kind of make sense of what we're seeing and figure out how far away they are and how big they are. So identify them and looking at their properties and connecting those symbols of galaxy populations through cosmic time, and then ideally, explaining the changes that we see. So that's the basic premise behind drive my research. But more specifically, what I study are massive galaxies. Okay.
We can read it.
Okay, I'll get used to that. So massive galaxies today are kind of boring, maybe. Depends on who you ask. But I think in a lot of ways they're kind of big. They have really smooth, kind of relaxed stellar bodies. They have red and dead stellar populations. And all of this suggests that they were formed a very long time ago and have just kind of sat there. They're basically relics of a much earlier epoch when their stars were formed and maybe when their structures were kind of settled. So this kind of, they suggest a weird monolithic collapse version of the universe, at least in their history. And so we can ask the really simple question, if we were to look back in time 10 billion years, what do we think these galaxies would have looked like? So here's my red and dead nearby elliptical galaxy. And if I look back in time, if it is a relic of an earlier time period, it might look approximately the same. But I can be a little bit more careful than that because I told you that the stars were red and dead. 10 billion years is a long period of time, even for a galaxy and even for stars. So I'll modify that by saying, well, maybe they're a little bit bluer. The stars are a little bit younger. And the surprising thing that we found was, people went back in the last decade and they looked for massive galaxies 10 billion years ago, and this is not what they saw. What they saw was something more like this. So yes, the stars were much younger, the colors were bluer, but the structures of massive galaxies, when you look back in time 10 billion years, were much smaller. They were structurally different. And this was kind of a surprise, and this caused people who study massive galaxy evolution, first of all, to get excited about it. There's something happening that wasn't what we expected, and that is good. Because maybe it means that I have a job for the last 23 days. And so now we have a really interesting field of study. We can ask we can ask questions about how this evolution occurred. We can be a little bit more careful and quantify that evolution. And so here I've given you, so this is the same image. This is NGC 5846, and if you want to hear a really exciting story of what you should do to your grad students in their first project, I stared at this for 8 nights with the 1-meter telescope at CTIO, so I can tell you all about that. I have the deepest image, probably, of that galaxy. But in other respects, it's not a particularly interesting local galaxy. It's on the outskirts of the Virgo cluster. So here are the properties of the local massive galaxies that I mentioned earlier. And here's a big picture of maybe a similar galaxy 10 billion years before, so Redshift 2.6. And so if we want to study the evolution of massive galaxies, then we have to find those similar galaxies through cosmic time and then study their properties. And so we might want to look at similar galaxies in their sizes, but I've already told you why that might not work. We could look for similar galaxies in masses, so galaxies with similar masses through cosmic time. We could look for other red galaxies at earlier epochs, and we could look for galaxies that have these smooth, divocalar, spheroidal morphologies. This is more of a challenge than you might think, just finding the progenitors of massive galaxies. And part of that is because the last 10 billion years have been really, really busy for massive galaxies, and all of those properties that I listed have been changing. So in addition to their smaller sizes, which I did mention, massive galaxies at higher redshifts were less massive. They have grown in mass, and I'll tell you a little bit more about that. Many of the galaxies were not red and dead, but in fact many massive galaxies at redshift 1 or greater were still forming stars. And so if we just identify progenitors as the already quenched galaxies, we'll be missing large populations of galaxies. And finally, this is kind of a jargony term, but basically the distribution of stars within the galaxies seems to have evolved strongly, and I'll show you what I mean by this. But that means that instead of being characterized by divocalar profiles, they have lower Cerseic indices. They just have a different shape for the density profiles. So I'll go through and show you some of the evidence for all of these assertions. Okay, so this is a plot from my first paper where we showed the distribution of galaxies. Local galaxies here are open symbols, and these filled stars are 9 galaxies at redshift 2 in size and mass. So you can see that, well, first, there's a size-mass trend for all galaxies. More massive galaxies are bigger. But there seems to be an offset between the size at a given mass for local galaxies and the size at a given mass for high redshift galaxies. So this is just to kind of motivate that this wasn't just some freak galaxy that I've shown to you. And this is early evidence. This has been reproduced by a number of different studies. Yeah?
How do you determine the masses?
So these are stellar masses. And these are determined by fitting the spectral energy distribution with stellar population synthesis modeling, and then assuming that mass to light ratio and multiplying it by the photometric luminosity. This has also been demonstrated with dynamical masses. So if you look at the evolution at fixed dynamical mass, there is a discrepancy in the sizes of massive galaxies. But for this is photometric stellar masses. And so the other thing that we did that you can see from these kind of arrows is, given this offset in the size mass plane, we made some simple calculations using the very simple Varial Theorem arguments that estimated, how a galaxy might evolve in this plane, in size and mass, given a number of different physical mechanisms. But these are very, very simple estimates, and I'll show you in a second that we can do a slightly better job. The other thing that's really interesting about the way that this size growth occurs is that it's not self-similar. Every part of the galaxy doesn't just kind of puff up and grow with time, but instead, here I'm showing you the density profile of massive galaxies in grayscale, so black and gray here. These are high redshift, the same 9 high redshift galaxies that I showed on the previous plot, and in different mass bins, local elliptical galaxies. And what you can see is that if you were to fit a profile to this and fit a size of these galaxies, the size evolution is quite different. That's what I showed you on the last plot. But in the central regions, the density is actually pretty similar. And so that most of the size evolution is driven by an increase in the density in the outskirts of the galaxies. And so basically, the central cores of local elliptical galaxies are very similar to their high redshift progenitors. And most of the size evolution is driven by a buildup of an outer envelope. And we suggested that this is, primarily driven by minor merging in a cosmological setting of massive galaxies. That's not to say that other processes aren't occurring, but minor merging can have this effect where it builds up the outer envelope preferentially. But I'd like to be a little bit more careful and tell you more about the way that we could figure out those arrows, figure out how galaxies are also evolving in mass as they evolve with size. And this is especially important because if you merge 2 galaxies together, you know that their mass gets larger. So it's important to kind of build into your understanding the fact that you allow for galaxies to evolve in mass. So one way to do this, Casey's name is in the cutoff part, but a number of groups have done this.
Unintentionally, I'm sure.
I apologize. It's probably right about here. But a number of people have done this, which is that you can use the evolution of the mass function to constrain the mass evolution of a population of galaxies. And so I'll give you a really brief description of this if you're not familiar with it. So here I'm showing you the cumulative number density of galaxies as a function of mass. And you can see that this, in my cartoon, evolves with time. And so just to illustrate, if every single galaxy grows in mass at the exact same rate, then that corresponds to just a shift of this entire function with time. If instead you have a differential evolution in mass, and so some galaxies evolve more quickly in mass than other galaxies, then you could get something like this where there's a buildup. If you have low mass galaxies growing really quickly and high mass galaxies not changing very much, then these galaxies would move in mass more than these galaxies, and you would get a change in the slope of this relation. And so this kind of formed into the idea where if instead of making comparisons between galaxies at fixed mass, instead you make comparisons of galaxies at fixed cumulative number density, then this somehow identifies a similar population of galaxies through time. So there are ways in which this can break down. For example, if you have a galaxy over here that evolves very rapidly and overtakes other galaxies. But for the most part, this is certainly better than assuming that galaxies don't evolve in mass, and has been shown by several groups, by making comparisons to either semi-analytic models or other kind of analytic models, that this works fairly well to determine the median or the average properties of galaxies. So if we do this, if we play this game and make a cut in fixed cumulative number density, and assume that we're then kind of getting an idea of what the average growth of galaxies is at that number density, then we can get an idea of how much that population of galaxies has evolved in mass. And if then we identify, so if we take a slice, a small range in mass that corresponds to that mass growth, you can see here's the mass growth, and then if you look at the size evolution of galaxies within that redshift evolving mass slice, then you can also see that the size of those galaxies evolves even as the mass evolves. So in this particular paper, this is Peter Van Dakken's 2010 paper, this has been repeated, particularly by Shannon Patel with the candles data. But you can see that this corresponds to a factor of 2 growth in mass and a factor of 4 growth in size for this particular number density. This depends on the population of galaxies. Lower mass galaxies will have very different evolutionary histories than higher mass galaxies. If you can see, these are, this is 10 to the 11.3, 10 to the 11.4. These are really massive galaxies. But the interesting thing is that now we've designed a way to follow a population of galaxies, not through 2 different snapshots, but actually kind of smoothly through time. And when we've identified those, this is essentially the same plot that I showed you before, just the density profiles of galaxies. You can see that this evolution of the profile shape occurs really smoothly with time. And so I mentioned the Cerseic Index. This is this Cerseic profile. And the Cerseic Index is this N that basically describes the shape of the profile. And what this corresponds to is, yes, the color scheme is reversed from what you'd like it to be, because the lower redshift is redder. But if you forgive that, then at high redshifts, you can see that this corresponds to a Cerseic index of closer to 2. And at low redshifts, you get a high Cerseic index. This is a really smooth evolution, which is great. The last point that I mentioned, and this is slightly in a different direction, but it's really important, I think, when you want to describe the evolution of massive galaxies, is this point that I made that at low redshift massive galaxies all have dead stellar populations, but at high redshift this is really not the case. So this is from Adam Muzzin's 2013 paper. Yes. So here what I'm showing you, I'm switching to number density, not density. So this is the mass function at low redshift and the mass function at high redshift. And I'll just highlight, here's 10 to the 11, these are massive galaxies. And at low redshift, this is the quiescent fraction, so just take a step back. The blue mass function here is the number density as a function of stellar mass for galaxies which have been identified to be still forming stars. And the red is for galaxies which are, which we would call quiescent galaxies, so no longer forming stars. And you can see that the distribution of galaxies depends pretty dramatically on their star formation properties. And if you divide those, you can get a sense of what fraction of galaxies are still forming stars and what fraction of galaxies are not. At low redshift, at high mass, almost all galaxies are quenched, are no longer forming stars. So most galaxies are in this red mass function. However, at high redshift, so redshift 1.5 to 2, this changes dramatically. So here's the low redshift distribution, and at 10 to the 11th, there's this crossover happening. This is 0.5. Sorry, the number got cut off. But half of these galaxies are still forming stars. So if, for example, as you follow galaxies through cosmic time, you're only comparing quenched galaxies to quenched galaxies, then you're really missing a large portion of the progenitors of those massive galaxies at low redshift. Yeah.
Adam's error distribution on the left-hand quiescent fraction is pretty large. Is that
Yeah.
just from resampling the function? I mean, if I just kind of look at the plots.
It's huge. I think, look at you can see the errors here. I think this has to do with just, low numbers of galaxies.
Just to resample it over and over again, you get different quiescent fractions.
Yeah, but
It's naively, expects to be much better.
this seems insane,
Yeah.
actually. This is not just the SDSS mass function, and I think maybe if you looked at Redshift search, I would hope you could do a better job of this.
Right.
But when you go to lower Redshift than this in SDSS, 10 to the 12 galaxies are pretty rare, but.
Yeah, 10 to the 11 are pretty common.
Yeah,
so-
I mean, this error bar right here seems a little bit nuts to me.
Right, because it's almost overlapping with one of them, right?
Correct.
So,
But, I know Adam pretty well, and he's pretty conservative with these things.
Yeah, it's a
So
question mark for
that's kind of that's my guess.
On the x-axis in the right-hand plot,
Yes.
the leftmost number, is that really 8.2? It seems like
Yeah.
a phantom digit.
Yes. So this is a multi-panel plot. This one.
Yeah.
It's a multi-panel plot, and I'm only showing you 2 of 4. So this is
Well-
the intermediate redshift ranges. I hate having like a million plots on one.
Oh, I
One
see.
screen.
Oh,
Where-
it's
Well, from the
the
other edge.
right-hand edge of another.
Yeah,
I
where
see.
all I want to do is highlight 2, so I cut them out, but it's true. So I'm going to give you a break, and hopefully you can see this. Just to give you an idea from a simulation of what I mean by growth via minor merging in a cosmological setting. So this is a simulation by Thorsten Nabb's group of the formation of a massive galaxy. And you can see that this galaxy doesn't undergo very many major mergers. By major merger, I mean a merging event with a galaxy that is within a factor of 1 to 4 in mass. You can see that there are a lot of merging events with smaller galaxies, and some of these smaller galaxies are probably pretty large in this simulation. It's just that the central galaxy is much larger. And if you look at the outputs from these simulations, what you see is roughly a similar inside-out growth. So the central core density gets formed early, and then the outer envelope builds up. Now, if you were to tag particles, that's not to say that every single star in the central core of the progenitor galaxy is in the same place that it was at early epochs. So there is some kind of moving in between the central and outer parts of the galaxies. But if you look at the net density profile, you see this inside-out growth. So I'll shift gears a little bit and talk more specifically about the things that I've been working on more recently. And ask the question of, if I fold, what else can I learn if I fold galaxy dynamics into this study of the evolution of massive galaxies? And when I say dynamics, at high redshifts, I mean velocity dispersions. I don't mean rotation. I would love to tell you about whether these little tiny guys are rotating. That would be awesome. We don't have the technology to do it. Part of it is that they're tiny. And so in order to resolve the kinematics, you have to be able to resolve the galaxy, and you need to be able to do it with an excellent spectrograph, with excellent seeing, probably with adaptive optics. Even to measure their sizes, we really need to go to space. And so what I mean, and furthermore, it's been suggested that they might be kind of more disk-like. So, but to answer the question about whether they are rotating is something that's kind of out of reach at this point. Really, really quick reminder. When I say velocity dispersion, because these galaxies are kind of dispersion dominated, that means you can kind of imagine stars moving around like bees in a swarm. And that kind of makes up the galaxy, and you measure that directly from the Doppler shifting of their features. So you can see that their spectral features, their spectral features broaden as the velocity dispersion of the stars gets larger, or the bees swarm faster. And so, okay, so that's really simple. What do we expect for the dynamics of those galaxies? Really simplistically, everybody knows the Varial Theorem. You don't even have to read Binney and Tremaine to get the Varial Theorem. The Varial Theorem just says that the potential energy of the galaxy is going to be balanced by the kinetic energy of the galaxy. And so given that the masses of the galaxy are changing, but not as rapidly as the sizes are changing, one might simplistically predict that their velocity dispersions, if we look at the baby pictures or baby spectrographs, then we might see much higher velocity dispersions of these progenitors of massive galaxies 10 billion years ago. On the other hand, the Varial Theorem actually has to do with enclosed mass. It's not the total mass necessarily of the galaxy. Part of that is because when you measure the velocity dispersion of the galaxy, you're measuring essentially a luminosity-weighted velocity dispersion. And so most of the light is in the center. And so actually you're dominated by the central mass. And since the central density, I already showed you, this is the cartoon version of the plot that I showed you before, since the central mass is fairly stable, then actually one might expect that the velocity dispersions of those galaxies haven't evolved significantly with time. So here I'm just taking the Varial Theorem. So this is velocity dispersion growth factor, taking the measured mass, size, and Cerseic Index evolution, using this cumulative number density evolution trick from Peter van Dokken's work. If I just take the evolution in m over r, so just taking the simple Varial Theorem argument, this black line is the evolution that I get from redshift 2 to redshift 0. So time goes to the right here. And you get that at high redshift, you'll have a higher velocity dispersion than at low redshift. That was the simple plot that I showed you before. If instead I take a model that builds in the shape of the density profile, so in the form of this Cerseic Index, and estimate the constant that goes into the Varial Theorem as a function of that density profile shape, then actually the red line is what I get for those mass and size and Cerseic Index evolution. And so in that case, assuming that we believe these models, et cetera, then you get roughly constant velocity dispersion with time as these galaxies grow through this inside-out growth mechanism. So,
But the black line,
yeah.
was no evolution.
This is no evolution in the Varial constant. That's this
So your
situation.
Cerseic Index would be 2 the whole time.
Or 4,
So
or
no mass,
whatever it is.
and no
I'm assuming
rate of
Varial,
change.
yes, I'm assuming Varial constant of 5.
So why is it good down?
Oh, sorry, this is with time.
Right.
So the mass evolves as a factor of 2, and the size evolves as a factor of 5.
Okay, so you are allowing the size and mass to grow.
Correct.
Okay, okay.
Yeah.
So it's not no evolution.
Right, yeah, sorry, this is
Got it. So
this
you
is
take
just the
mass and
size
distribute it
evolution.
over large area, that's what you're saying.
Yes,
Got it.
this is the density evolution, essentially. Okay, so now I've kind of primed you for this, for including the dynamics into the study of massive galaxies. So this is part 2. We'll shift to talking about the structures of massive galaxies and their dynamics. And we know this very, very well. When you incorporate the dynamics and the structures of galaxies, this is called the fundamental plane. And so on the vertical axis here, surface brightness, velocity dispersion, and size, effective radius of the galaxy. I'm going to show this to you in both 3-dimensional and in 2-dimensional space, because I do not think in terms of 2-dimensional projected fundamental planes, and I don't expect you to either. So if I look at the distribution of massive galaxies in this 3-dimensional space, this is not new, by the way, what you can see, so I'm showing you longitudinal sky survey galaxies in this small redshift slice, some Cerseic fits to give you the sizes of the galaxies. I'm only showing you red sequence galaxies for this, and actually for most of this part of my talk, and we can talk about this more. But a number of people, and in the late 80s, noticed that galaxies don't fill up this space. Galaxies reside in a very thin plane in this 3-dimensional space. And so just to kind of show you this, this is a sort of recent measurement of the plane of these galaxies. This is the Heiden-Bernardi fundamental plane. And you can see that if you draw this out and I, spin it around, you can see that galaxies really lie in a tight plane in this three-dimensional space. They're not spreading out. And so this is more similar to the view that you would normally see in a paper, but luckily I can kind of rotate it around so that you can see. So this is at low redshift. And we can ask the question, I'm certainly not the first person to do this, of what happens to this fundamental plane if I include galaxies at high redshift. So what I've done is I've put together a sample of galaxies from the literature here. And this list is sort of, in order to include galaxies from the literature in this sample, I've basically taken any set of galaxies for which there are measured and published dispersion measurements, and for which I can match to a photometric catalog for this project. And that becomes really important in the next slide. I have a new sample that I'm including here. This sample has about 100 galaxies. It's actually about 150 galaxies at a redshift of 0.7. And these galaxies are selected by inferred velocity dispersion, square root m over r, basically. So from photometric catalogs in the Newform Medium Band Survey and the UDS field. And they're selected as such because I hope to be able to measure dynamics for those galaxies. I measure I have spectroscopy for these galaxies using the DEMOS instrument on Keck. It's about, depending on the mask, it's about 10 hours per mask. So it's a lot of time. These are really deep spectra. These are deeper than deep. So it's using the deep instrument, but it's much deeper. And so for most galaxies, I can measure dynamics down to 100 kilometers per second. I'm not really measuring reliable velocity dispersions. For this, I'm only showing you galaxies that, based on their colors, are quiescent for a fair comparison with the low redshift sample, and because including the star-forming galaxies complicates things quite a bit. And I'm also only including galaxies for which I'm measuring velocity dispersion within a 10% error. So these are really reliable dynamical measurements. Okay, so what happens if I put high redshift galaxies onto this? Well, high redshift galaxies, these are color-coded by redshift, no longer lie on the same fundamental plane. They seem to, yeah.
Wait, unless I have an honest question, but maybe I'll let you talk.
Okay, this is an answered, this is a solved problem as well. And so that might be your next question. This is a solved problem. This is actually very easy to explain because on the vertical axis I have surface brightness. Or, I don't know what axis you want to call that. But on this axis you have surface brightness. And even as I showed you at the beginning, these galaxies, the stars in the galaxies are evolving. And as a stellar population evolves, its colors, but also its surface brightness will evolve. And so this is explained, you can see that the color coding is with redshift, so the highest redshift points are the furthest away from the plane. That's because their stellar populations will fade, essentially, onto the local fundamental plane with time.
This is consistent with that? I mean, what you expect? It's a redshift 2 and a redshift 4 point.
It seems to work quite well if you just take simple models. So a number of people have done this out to redshift 1.2-ish and have done the modeling, and you can do things like constrain the initial mass function and constrain the formation, epoch, or the average formation epoch for massive galaxies. Jesse Bezanson is actually working on this question of modeling this evolution, and it seems to be fairly consistent when you correct for the selection effects at high redshifts. Otherwise,
obviously you can all kinds of progenitor bias from this too.
It's really weird unless you correct for the selection effects. Okay. So this is what you might be more familiar with, the projection of the fundamental plane. But essentially this is the same exact galaxies. I'm just projecting it so that you can see the edge-on view. And so here in this axis, we've got a combination of velocity dispersion and surface brightness. And on this, it's just size. And so this is the Sloan distribution in the fundamental plane. And you can see as you go to higher and higher redshifts, galaxies just evolve off of the mass fundamental plane. But what wasn't done, or what wasn't fully understood during earlier studies of the evolution of the fundamental plane is this size evolution. Because in addition to the fact, that you have size evolution, and it's not immediately obvious how galaxies will evolve in this plane, because so the surface brightness and size evolution are actually correlated because you're measuring them with the same technique, essentially. So it depends on your profile shape. And the dispersion actually also depends on that profile shape. And so it's not as simple as you might initially expect given this dramatic size evolution of massive galaxies. So it's been suggested that this isn't just an evolution of the mass to light ratio, but that it also incorporates the evolution of the sizes, that this evolves, so that size evolution, one way to put it is that size evolution doesn't evolve you strictly within the fundamental plane. Size evolution might evolve a galaxy perpendicular or somehow tangential to the fundamental plane. And so what we've done is to go about testing this in one particular direction. So I told you that I've matched all of these spectroscopic samples to photometric catalogs, and excellent photometric catalogs. So this is the great thing about the field of galaxy evolution right now. We have awesome data. And so I've matched them to these photometric catalogs, and so I can get the best possible estimate from fitting spectral energy distributions of their mass to light ratios. And so what I've done is I've replaced the surface brightness, which was on this vaguely vertical axis, with stellar mass surface density, just multiplying the surface brightness with the mass to light ratio. Here you can see that this forms mass fundamental plane. This is also not new. People have studied the mass fundamental plane. And you can see that this, when I add high redshift galaxies, this is a really bit different picture than you saw with the evolution of the fundamental plane. So I've just flipped it around so that you can see, but primarily the high redshift galaxies are now lying with the low redshift galaxies. And this is interesting because this incorporates the mass to light evolution. I've, in a sense, corrected for the mass to light evolution. So here in projection, you can see this really dramatically. So here's the mass fundamental plane, low redshift, high redshift. And this is really remarkably stable relative to what we saw, where the luminosity fundamental plane actually, in a sense, was in place at high redshift, but there was this 0-point evolution. And by correcting for the mass to light ratios from photometry, I've actually accounted for that mass to light evolution, and it seems to work very well.
I mean, it's moving along, this relationship. This is correct.
Correct. So the evolution, in this case, must move within the mass fundamental plane. So just to highlight this, same scale on these two plots. Here's the luminosity evolution of the fundamental plane, the traditional fundamental plane, and here's the stellar mass fundamental plane. And so the fact that this is remarkably stable means that, to first order at least, it's a very good approximation to model the luminosity, the evolution of the luminosity fundamental plane as an evolution of the mass to light ratios. Okay. So for the skeptics in the audience, what this says is that galaxy evolution evolves within the fundamental plane. You can ask the question of whether this is surprising. And if you're really snarky, you can ask whether this is just the Varial Theorem. And both are fair. So to answer the question of whether this is surprising, there have been simulations. So this, I'm showing Brant Robertson's work, but Mike Boylan-Colchin has done similar simulations where you take galaxies and you merge them. And the main result is that once a galaxy is on the mass fundamental plane, in simulations essentially it stays on the mass fundamental plane. But the thing that you have to add with an asterisk is that it's not clear whether these simulations also reproduce the size evolution, realistic size evolution that's now observed, or whether the simulations, these are not cosmological simulations. And so whether a simulation that incorporates all of the minor merging that may be important in driving the inside-out growth of galaxies, it's not entirely clear that this result would stay the same. Other formation mechanisms, so this is an older result where the mass fundamental plane is essentially formed, and the tilt of the fundamental plane is formed via dissipational gas-rich disk mergers. And so this is slightly fallen out of favor in terms of formation mechanisms for massive galaxies, and it's just unclear to me whether other formation mechanisms can produce such a tight relationship. So this is ongoing question. But I don't think it's entirely, I think it's a little bit surprising, I guess, is what I would take away from this. It's not entirely a given that this would be the case. So I'll really quickly go through answer to the second question of whether this is just the Varial Theorem. And so here I'm basically showing the fundamental plane was essentially explained as being understood as both the Varial Theorem and also a distribution in mass to light ratio as a function across galaxy properties. So that's called a tilt, but all that means is that high luminosity galaxies have different mass to light ratios, dynamical mass to light ratios, than low mass galaxies. So what I'm showing you, this is the edge-on projection of the luminosity fundamental plane and the scaling that one might expect from the virial plane, and in red. So the mass fundamental plane is edge-on, and you can see that the virial plane is slightly different from the luminosity fundamental plane. So this was explained by Sandy Weber in the late 80s as that with that tilt. But this could also be caused by, and I've given a million references, it could be non-homology in galaxy structures or their dynamics, it could be initial mass function variations, and it could be variations in the dark matter because velocity dispersions feel dark matter as well, whereas surface brightness and sizes do not. So the mass fundamental plane, yeah, just showing you that those are tilted with respect to one another. The mass fundamental plane is much closer to the luminosity fundamental plane. So this is the edge-on view of the mass fundamental plane, and the red is the virial plane, and they're very, very similar. So in a sense, you could say, to first order, this is very close to the Varial Theorem, but it's not exactly the Varial Theorem. So you can see, they're not exactly the same plane. This is where the 3D helps me a lot, at least. And if I project it and look at the evolution of the dynamical mass to stellar mass as a function of dynamical mass, this tells you about the deviation of the mass fundamental plane from the virial plane as a function of dynamical mass, then you can see that there is this variation. It's very nearly the virial plane, but it's not exactly. There is this tilt. So Hyde and Bernardi measure a tilt. It's very similar to what I get. That's good. It's very similar data.
What IMF?
This is Chabrier IMF.
Chabrier.
I'll come back to that in a second if I have time. This is really, really hard to do, though, because selection effects dominate how you measure this tilt. So same data, but I'm color-coded by all of these different properties that you might use to cut your sample. So stellar mass goes at a diagonal. Magnitude is even worse. It goes at a diagonal in this plane. Size goes at a diagonal. Velocity dispersion, a different diagonal. Cerseic Index kind of cuts across here. And so if you make cuts on any of these things, your selection effects are going to dominate the tilt that you measure. So I put this up here because I haven't measured it super carefully. You have to model all of these things very carefully.
Spectroscopy data, all, especially RBM, surface brightness, they all have fallen. Right.
Yeah, but I mean, there's going to be an effective magnitude threshold. You know, below which or above which in magnitudes, you wouldn't get this signal to noise.
Right, it's really a surface brightness.
Yeah, it's
Right.
essentially a surface brightness question. Anyway,
Right.
it's just tricky. You have to fully model all of the biases in your sample to measure the tilt. Furthermore, it depends on how you look at this. So if instead of looking
Sorry, I
at...
don't interrupt, but
Yeah.
does it, I can't picture naively, it's the cold medication.
Yeah.
I mean, if you imagine, do the selection effects go in the right direction? That's what you expect them to correct toward the fundamental, the varial.
So
Theorem.
the Varial Theorem would be horizontal, a horizontal line on this plot,
Horizontal, okay.
and tilted would be a diagonal line,
It tilts that
tilted
way.
up. This line, yes, no tilt.
Okay.
So this is the Varial Theorem, and this is the measured tilt of
So
the.
if the selection functions tilt you against the measurement, then it would. And
Correct.
naively, it might.
All of these selection functions tilt you towards measuring a tilt.
Right.
Yeah.
It depends on how you look also. So Haydn Bernardi find that this is tilted. Michela Capillari finds that the mass fundamental plane measured slightly differently is actually very similar to the virial plane, but he compares kind of to stellar mass. And if I look at the distribution of the dynamical mass to stellar mass ratio as a function of stellar mass, I see much less variation. So in this projection, it looks like it's not tilted. So it depends on how you look at this. You have to do this really carefully. But to first order, it does seem like galaxy formation is occurring within the mass fundamental plane. Caveat time. Or caveats or future work or however you want to think about it. We can do it more optimistically than that. So first of all, where do star-forming galaxies fall on here? I spent all of this time telling you about how galaxies are changing, and if you ignore certain populations, then you're missing progenitors and you're imposing this progenitor bias, and this is to be continued. It's just really hard to do at the highest redshifts because it used to be that galaxy spectroscopic surveys would be kind of split into the camp of people who looked at star-forming galaxies and the people who looked at quenched galaxies, and never the two shall meet. But I'm looking into this and working on this. It's a bit more complicated than you might initially think, but I do have this sample that includes star-forming galaxies. Many people have suggested that there is a non-universal initial mass function, or that the initial mass function of galaxies varies across galaxy populations, and this will fold in to the tilt of the mass fundamental plane with respect to the virial plane. So just to illustrate that, this is really a very simplistic illustration. This has to be done more carefully. But if, for example, I take Charlie Conroy and Peter Mendacum's measurement of the variation of the initial mass function relative to the initial mass function of the Milky Way as a function of velocity dispersion, there is this trend. And so throughout this, I've been assuming a Chabrier IMF. If I just artificially boost the stellar masses as a function of velocity dispersion in this sample, this is the plot that I showed you before. You can see the tilt of the fundamental plane with respect to the virial plane. If I just boost the velocity the stellar mass to light ratio of high velocity dispersion galaxies, this is what I get. So it's removed this tilt, and galaxies are within a virial plane. Really simplistic. There's got to be a better way to do this, but it is very important for looking into the cause of the tilt of the mass fundamental plane.
Makes the stellar masses go down.
It makes the stellar masses
Sorry, no, I misread that. It makes them go
Yeah.
up.
yeah,
Yeah, it's true.
at the high dynamical mass end.
But right, sorry, that's what it is. But it's all the change at the low mass at the bottom? Yeah.
This is higher too, so it kind of, it shifts these up and it shifts these down. I have a really hard time visualizing stuff.
Right.
Anyways, this is a really important thing to do carefully, not just, fitting a line to this. But it does become really important. Finally, dynamics of galaxies probe not just the stars, but they probe the dark matter. And as you have this evolving dark matter profile and evolving sizes, you're actually sampling a very different, well, sort of different part of the dark matter density profile. And so it's been suggested that actually your dark matter fraction that's enclosed within your aperture within which you're measuring your dispersions or the effective radius of the galaxy would evolve. And so this is from a simulation from Hills, from Thorsten Nab's group. Just the dark matter fraction is a function of stellar mass of galaxies in merger simulations. And it depends, this dark matter fraction depends both on the stellar mass of the galaxies in the simulations, but it also depends on the mergers that these galaxies that have been having. And this is because the mergers, the mass ratios of the mergers actually determines the shape of the density profiles. So this inside-out growth is really important because it also has different implications for the enclosed dark matter fractions. So in order to really model this evolution within the mass fundamental plane, you want to include these evolving dark matter fractions. And that is really hard to do. But it's something that I'm thinking about. And finally, I'm an observer, unless you forget that. This is really important to have more representative samples at high redshift. So I mentioned kind of off the cuff that you need to correct for selection biases when you study the evolution of the luminosity fundamental plane. But just to, there were 6 points on my highest redshift plots, and I'm an astronomer, so I'm allowing to put a line through those 6 points. But to really sample the distribution of galaxies at higher redshifts is going to be really important. And maybe that's not at redshift 2. Maybe that's something that we do initially at redshift 1. But this is really important for future studies. So I'll leave you with 2 things, and it's kind of a contrast between the dramatic evolution of massive galaxies in the last 10 billion years, and in contrast, the kind of stability of the mass fundamental plane, which, all of the caveats that I mentioned are folded into that, but essentially, to first order, galaxy evolution seems to be fairly regular. It seems that galaxies, red Binnian terrain, are aware of the Varial Theorem and are essentially evolving within this mass fundamental plane, even though that evolution is fairly dramatic.
Thanks, Rachel. Questions for Rachel?
So you mentioned studying the mass fundamental plane for star-forming galaxies. Is that called the Tully-Fisher?
So it's similar to the Tully-Fisher. If you're going to put them on the mass fundamental plane,
because then
my guess is my samples, I'm only selecting samples for which I can measure a velocity dispersion. And there's this threshold between where you would call a galaxy a star-forming disk with a small bulge and what you would call a star-forming galaxy with a big enough bulge to have a dispersion. And so it's intertwined, and it's a really tricky dividing line. It's very similar to the Tully-Fisher relation, but
so you'll be targeting like S0s, or let's say.
So there'll probably be S0s, or there'll be the recently quenched galaxies. There's going to be a period of time where galaxies might be dispersion-dominated galaxies. Morphologically, they would be kind of progenitors of S0s or elliptical galaxies. And they would have dispersions, measurable dispersions, and would probably fit better onto fundamental plane relation than onto the Tully-Fisher. But it's true, that's one of the tricky aspects, is knowing when you're measuring dispersion or unresolved rotation.
But it's got to be fundamentally just dynamical mass, right? I mean, so here, just because these are all dispersion dominated galaxies, that it works. If we went to a disk, I mean, you can imagine a completely coherent rotation, you would do zero dispersion. But it could
Although
still
many
set
of
up
these
the
galaxies
anomaly.
have low Cerseic indices.
Right.
And I'm not correcting for that discrepancy in the Varial constant as a result.
Okay.
So there is that evolution, and non-homology is going to move things within that mass fundamental plane,
Sure.
and dark matter fractions, and everything is in there. And I think to tease out those different effects, actually it'll become important to include star-forming galaxies.
Right.
Where the deviations are.
And correcting for this rotation factor, because you have that.
Right, and at intermediate redshifts you can correct for the
Right,
rotation.
Who is it?
So Ari and Vanderwall has resolved kinematics of
Ben and Susan Cass have done some of this, where they have some proxy for dynamic. It's like a pseudo velocity expression where they fold in the effects of rotation.
Well, it's like a square root of 2 factor.
Right, one's rotation, one's dispersion.
Yeah.
But I think they're measuring that both from emission lines. I can't.
Right,
remember
so that's really tricky. This is all absorption line kinematics.
Right.
I can measure absorption line kinematics of star-forming galaxies, but I'm still trying to quantify, where that works best.
Yeah. Seems like it has to be a dynamical thing. It's not. I mean, it works for dispersion because of the
Right.
this type of there. I have one. I'm trying to remember exactly where it came up from. A short-term memory. I think it's failing here right now. Well, it's going to be about the IMF. I think I'm going to ask you that later. I'm really going to open that can of worms here.
It's a really big, I debated whether I should even open it, but it's really important for this.
Yeah. All right, I'll go ahead and ask it. So, I mean, when they measure the change in the IMF, they're really doing it like 1/8 of the effective radius or something like that. And you can imagine, so if it's going to work to correct this, then the small things that are building up the outer isotopes have to know what the IMF of the stuff in the core of these
Yeah.
halos. And is that really?
I mean,
There must be some. I know people like Peter and Charlie want to really go out and measure the IMF in the outer isotopes with the.
but
surface radius too
it's
low.
right. I mean, it's a contrast issue. They're measuring the faintest
Yeah.
stars, and
They have to
when
do it
you
in the
come
core
out
because
skirts.
they can't measure it.
Um,
I mean, if you've doubled the mass of something where the inner IMF is, I don't know, saltpeter, super saltpeter.
Right,
you're
and
adding
the
stuff that's
outskirts
Chevrolet.
are tiny things. They
Yeah,
have to
so
have
then
a
the
different.
average, yeah, it's good. Right, exactly, they're, right.
So the thing that might save this is that, you measure your velocity dispersion kind of, and it's dominated by the central regions as well.
So interesting, okay. So in some sense it doesn't matter because your
Maybe,
mass weighted
but on the other
velocity
hand,
dispersion.
if you assume that the mass is growing by a factor of 2, and that mass growth is dominated by these tiny things, which have a totally different IMF, I think that the answer is that you need to somehow have a measure of the IMF at higher redshifts, another point to compare the luminosity weighted IMF. Because I think, you're always going to be dominated by the central regions.
I don't know,
It's
worth
really
thinking about.
hard, but I think it's
That's why I
really
didn't ask,
important.
yeah, necessarily here, because we could probably talk about it for an hour, so, okay. Any other questions? All right, a few of us are taking breaks for lunch. I think we have graduate student harassment scheduled at 4:15 because it didn't collide with anyone else's schedules or minimize the number of collisions. So feel free to talk to her then, or you can come find me and I'll tell you where she is if you want to talk to her some more. So let's thank Rachel again. Yeah.
I almost emailed the boy at the first